In this video we're going to be looking at a slightly more advanced sequence than some of the simple ones you might have looked at already. In this case, an is n factorial over n to the n. And the issue here is to look at its behaviour and see whether it converges, and if it converges to find the limit as n goes to infinity. Well, this is one of those sequences where actually it's not a common thing, but it's useful to look at some actual numbers to see just how it's going to behave. How does n factorial behave when compared to n to the n? So if we were to actually put down a little table of values n factorial n to the n, just to see what sort of thing happens, well, for n is 1, n factorial of course is just 1, and 1 to the 1 is 1, not telling us anything. N is 2, 2 factorial is 2, and 2 to the 2 is 4. For 3, n factorial is 6, and 3 to the 3, 3 cubed is 27. 4, well, n factorial is 24. 4 to the 4 is 16 squared, it's 256. So it's beginning to look already as if n factorial is growing much more slowly than n to the n. So our suspicion is that this sequence converges to 0. If you try n equals 5, 5 factorial is 120, 5 to the 5 is 3000 and something, it's much larger. So our suspicion is this thing is going to tend to 0. The question is, can we actually write down a convincing proof of that fact? Well, this is one of those occasions where you have to basically have a bit of a clever idea to see what's going on. But it's not too hard to see what's happening. Look at n factorial over n to the n factorial, 1 by 2 by 3 by 4 up to n, and n to the n is n times n times n times n times. So we can write an as 1 by 2 by 3 by 4 up to n, all over, well, n times n times n up to n. And there are n terms, numerator and denominator here. Of course, the two n's at the end cancel themselves off. The last term I would have here, I've not written down, n minus 1 over n. Well, I know that's less than 1. In fact, that's true for all of these terms. All these terms are less than 1. 2 over n, 3 over n, 4 over n. So if you pair them up, numerator and denominator, what you get is that this is less than or equal to, well, I'm actually going to leave the first one alone, 1 over n times, well, 2 over n is less than or equal to 1, strictly less than 1, in fact, but less than equals all we need. 3 over n is less than 1, and so on. Got a lot of terms that are less than or equal to 1. Well, clearly, that's just 1 over n, and as n goes to infinity, this thing will tend to 0. Now, an, of course, is positive, it's a collection of positive terms, so by the pinching theorem, since an is bounded below by 0, and is less than or equal to something that tends to 0 as n goes to infinity, an itself must tend to 0. So, by the pinching theorem for sequences, the limit as n goes to infinity of an is 0.